My name is Ryan Fortner, and this is my presentation of Physics 2211 Lab 3, Black Hole. First, I will go through the purpose of the lab and the key concepts dealt with in each part. This lab is split into two portions, each with its own code, results, and analysis, which I will go over as well. In Part 1, the purpose is to find the mass of the black hole using a computer simulation of the planet's motion and the net forces present. Then, in Part 2, the purpose is to calculate the spaceship's initial velocity and all forces acting on the planet and the spaceship, then use Newton's second law to make sure the ship and the planet move in their own respective trajectories. The first key concept is Newton's second law, which states that an object in motion will stay in motion until influenced by forces from its surroundings. It is also known as the momentum principle, where the change in momentum equals the net force times the change in time. We are able to manipulate this equation to find velocity or position at another point in time. The second key concept is universal gravitation, which is the non-constant force that describes the attraction of two objects with mass. It is given by the expression g times m1 times m2 all over r squared. It is negative because of the force's attractive nature, and it is different than gravity on Earth, which is m times g. The last key concept is parallel and perpendicular forces, and it is described using a derivative form of the momentum principle shown here. These forces are shown on a new coordinate system that uses p hat in the direction of motion and n hat in the direction of the kissing circle of the motion if the motion has curvature, and each force can be split into a parallel and perpendicular component shown here. For my code in part 1, I filled in the gravitational constant, which is 6.7 times 10 to the negative 11, the mass of the star, which is given as 2.0 times 10 to the 30, and delta t, which is the amount of seconds in one day. Then I filled in the formulas for the planetary momentum, velocity, and dp dt, its parallel and perpendicular components as well. From there, using the equation for universal gravity, I was able to approximate the mass of the black hole at each time point as the planet moves. From this code, I got F net to be 8.165 times 10 to the 28 newtons, the parallel component to be 2.43 times 10 to the 28 newtons, and the perpendicular component to be 7.81 times 10 to the 28 newtons. And my average mass of the black hole is 1.0 times 10 to the 34 kilograms. As shown earlier, net force is the same as the rate of change of momentum, and each parallel component and perpendicular component aligns to the other. This is explicitly stated in the momentum principle. This is why we are able to make assumptions and calculate the net force simply based on an object's motion. For part 2, I plugged in my black hole's average mass from part 1, as well as the previous initial conditions. After playing around with the simulation, I found the x and y speed components that allowed the ship to pass close to the event horizon and leave the system without crashing, to be -5 for the x component and 0.33 for the y component. Then I was able to sum all the forces to find the forces on the planet and the ship respectively. Here is a picture of the simulation of the planet's motion and the spaceship's motion after 1 hour. After manipulating the code more, I found another initial velocity that would put the spaceship into an orbit around the black hole instead of exiting the system. For the x component, it is -0.6, and for the y component, it stays as +1. I also increased the time frame to 3 hours so you could get a proper look at the orbit around the black hole. Thank you for watching my presentation.